sometimes we set new goals and try to achieve them. The force of excitement accelerates us, right? But while going on that path, some problems try to drag us backward. But the one who achieves success is the one who just walk on the path with a constant velocity, right? The problems will come, but the motivation will make us accelerated. When these both forces are equals to each other, we just go with a constant velocity and try to achieve our goals, right? Because we have started to go on that way, right? That's why we will just go with a constant velocity, and obviously we will achieve success at end, just like a spear falling through a Gibson and Jacobs viscometer, right? So before talking about the spear falling through some viscous medium, let us talk about Stokes' law, because this experiment is actually based on Stokes' law. So what is Stokes' law? When a body is falling through a viscous medium, it will experience a viscous drag. So what is viscous drag? When a body is falling through a viscous medium, a force opposing its motion, it means a force will try to just stop it. Just like friction, we know that when a body is traveling along this direction, a friction force will act along this direction. Means we'll try to just stop the relative motion. Just like this, when a body is traveling through a viscous medium, a fluid, a viscous force will act along the opposite direction of its motion. Means if the body is falling along this direction, a force opposing it will act along this direction, right? So this force is directly proportional to radius of the body and density of the liquid, and another thing that is really very critical thing, that is velocity of this body. Means the force will increase with increase in velocity of the body. But for small bodies, we will find a terminal velocity. First, let's talk about what is the amount of this force. So we don't know to which power of this term the force is proportional. So let us assume that is it proportional to eighth power of r, bth power of eta, and cth power of velocity. So we might have got it by heart that dimension of force is mlt to the power minus 2. Here dimension of r is L to the power a, eta will be ml minus 1 t minus 1 to the power b, lt minus 1 to the power c, right? So here we can say that L to the power a minus b minus plus c, m to the power b, t to the power minus b plus c. From this we can say that b will be equals to 1. Now minus b plus c equals to minus 2 means b plus c equals to 2, b equals to 1 means c equals to 1, and a minus b plus c minus b plus c means 0, a equals to 1, right? So now we can say that f is directly proportional to r to the power 1, eta to the power 1, v to the power 1, and taking equals to, we will get a proportionality constant k, r, eta, v. And experimentally it was found that the value of this proportionality constant is equal to 6 pi, means force will be equal to 6 pi eta r v, right? So when this body is traveling, let us suppose that this body is not freely falling, but falling through this medium, right? Then grounded downward force will act, means because it is falling, but a buoyant force will also act. The gravitational force and buoyant force will act on it. And now we have a viscous force opposing its motion. So for small bodies, after some time it will have a constant velocity, means the net force acting on it will be 0 because this viscous force will equate its downward force. So we know that the buoyant force is equal to volume into density of the liquid. Let us suppose the density of the liquid is rho into g, and the gravitational force will be equal to V into sigma, means mass of the body. Let us suppose the sigma is the density of the body into g. So the downward force will be equal to V sigma g minus V rho g. So when this downward force equals to this viscous force, the body will fall with a constant velocity and no net force acting on it. So we know that for sphere, volume will be equal to 4 by 3 pi r cube. So taking V and G common, we will find that 4 by 3 pi r cube. Let us suppose that the radius of the body is r into G. Taking this common, sigma minus rho equals to 6 pi eta rv. So pi will cancel. This will be equal to r square, and we are trying to actually find this terminal velocity, means at which constant velocity it will travel after this force equate, means what will be its limiting velocity, its critical velocity. Because when this velocity, the body will reach this velocity, the viscous force will reach this amount, and this amount will be equal to this amount, and when the net force is 0, the velocity will be constant, that is critical velocity or terminal velocity. So from this we found that velocity equals to, let me write here, velocity equals to 4 by 3 into 6, taking eta into r square g sigma minus rho, right? So we can say that velocity equals to 2 by 9 r square g sigma minus rho by eta, right? This is the velocity. Actually this is true for a medium like sea, like infinite amount of fluid is present. If let us suppose this complete room is filled with some fluid and I am dropping a sphere, there will be no disturbance. But when we use a Gibson Jacobs viscometer, means something that looks like that has a shape of a tube and has a length of 98 centimeter, has a radius of nearly 4 centimeter, means 100 centimeter cross radius is nearly 5 centimeter. Let us suppose that we have a Gibson Jacobs viscometer of this size. Then the wall and the end, means bottom of the tube, will affect the liquid flow, right? This will affect the liquid flow because they will also stick to that wall and hinder the natural motion. That will, if this room is filled with suppose a viscous medium, like suppose this room is filled with honey and I am dropping a sphere, the walls are very very at very large distance, and the motion of the sphere will not be affected by these walls, right? But infinite doesn't mean something like universe or multiverse, but it is something in comparison with something other, like for this pen, earth has a uh, earth is a infinite location, right? Infinite space. But for earth it is just a point, right? For earth is a point, and for the universe, earth is just like not for earth, but for universe, earth is just like a dot, right? But for us, earth is really very big, and here we are just talking about a infinite space, means infinite space filled with viscous liquid. But this is not infinite for a small sphere, so we have to apply some corrections, that is end correction and extent. Means the extent means the radius is limited and the length is limited, so we are going to apply a end correction which will have some value of the height of the tube and the correction due to extent or wall effect. To correct wall effect, we will need the radius of that tube, right? So the correction will make us get a accurate value, and this correction is there because we are just doing it in a limited space, not in a infinite space. I hope this thing is clear, and I hope you can answer why we apply this end correction, wall effect correction for wall effect to your external. So the end correction of end effect will be something like, if we are trying to find the actual velocity, it will be equals to velocity found into 1 plus 3.3 r by h, because end effect is due to the limited height of the viscometer, and which is h. And if we are trying to find wall effect correction, that is due to limited radius of this viscometer, we are going to say that velocity equals to v naught, that is the velocity found, into 1 plus 2.4 by 4 into r by r. Now I guess you are clear about this correction. So if we take this 2 common, then we will find that velocity will be equals to v naught into 1 plus 3.3 r by h into 1 plus 2.4 r by r, right? So you can actually, when a sphere is falling through a tube, we can calculate that. Let us suppose the ball is falling, it will travel this, suppose this is 30 centimeter. How much time will it will take to go from this position to this position? We can calculate it. Means we have the velocity, we have the distance, we have the time, we can calculate the velocity, means this v naught. We have now the equation, velocity equals to 2 by 9 r squared g sigma minus rho by eta. Eta is coefficient of viscosity. Actually the ball is falling through a viscometer. The name is viscometer, means we are trying to find coefficient of viscosity, not the velocity. We can calculate the velocity. Let us suppose a ball is falling, we marked some positions, and now we can see that how much distance it is traveling, and use a stopwatch to calculate how much time it takes. Means we have the distance, we have the time period, now we can calculate velocity. But the thing we can calculate with a stopwatch is coefficient of viscosity. So to calculate coefficient of viscosity, we just have to adjust this equation. Eta will be equals to, taking v to right hand side, eta to left hand side, 2 by 9 r square g sigma minus rho by v. We can say that velocity equals to distance traveled by time taken. So let us denote distance by h, s by t, t will come to numerator. Right, now we have this equation. So let's talk about the particular experiment we do in our labs. So let us suppose this is a Gibson Jacobs viscometer. We have some markings. You can just use two stopwatches and calculate how much time it takes to travel this much distance, then calculate for this much distance, then take an average time period, calculate distance, and you can do you can use two stopwatches and calculate this thing, but I'm just going to explain it for one, means for a single stopwatch, means for a single distance and single time period, and using that idea you can also extend it for more distances. That is, you can use 2 to 3 marks and use equations like this. Suppose this from actually one thing to be noted, that there is a space, there is some 10 to 12 centimeter left for sphere to fall, and then we start our stopwatch at this marking. This is because to let the ball actually attain the terminal velocity, because while falling there is acceleration, the velocity is increasing, but after traveling 10 to 12 centimeter, a small ball that is of 0.1 to 0.2 centimeter radius will get the terminal velocity. So remember about this space, and we also keep 10 to 12 centimeter gap from bottom, right? So I was talking about, if the ball, we have started our two stoppages at this place, then suppose to travel to this position it is taking 3 seconds, then to travel to this position it will take 6 seconds if these two lengths are same, right? Accordingly you can make your calculations and all, but now I am going to talk about, let us suppose let us suppose it is taking we are talking about this much amount of distance. So let us suppose it is taking 3 seconds to travel this 30 centimeter distance. So now we have distance, we have time, we can put it here. Distance will be equal to 30 centimeter, time period will be equal to 3 seconds. We know about G, 980 centimeter, 981 centimeter per second square, or we can say that 9.8 meter per second square. As we are dealing in CGS unit, so it is better to take G as 981 or 980 centimeter per second square. So actually this is my 9, this is G. I hope everything is clear. Sigma is the density of the ball or the sphere we are going to drop. Rho is the density of the fluid, and eta is the coefficient of viscosity we want to study. So here we have found that velocity is equal to actual velocity. Velocity found means actual velocity equals to the velocity we found multiplied by some corrections, right? That will be equal to 3.3 r by h into 1 plus 2.4 r by r, right? So we can, instead of v naught, we can say that v equal to v naught means this much distance is by time period multiplied with this, right? So here we can just take this thing and put it here, right? and then we will be able to calculate the actual coefficient of viscosity, right? So now we are clear about these things. Actually, when the body is traveling through the medium, it will just have to go against some forces. That's why these forces will be stored as energy in that body, and this energy will be converted into heat. Just like we know that when we rub our hands, friction force generates heat. Just like friction, viscosity will also generate heat. And sometimes when the body is traveling with a very fast velocity, some eddies, some waves get generated, and they also get stored as energy inside the body. But we don't need eddies and waves to set up when we are talking about Stokes law. Means Stokes law has some assumptions about the environment. So let us talk about experiment. We are just dropping our sphere. So here the sphere should be rigid, should be smooth, and the liquid should be homogeneous, but there should not be any boundary. Means there should be a sea of the fluid, not bounded by any limits, right? And there should not be any slip between the fluid and the sphere. Means the very first layer, means the just layer, just the outside layer of the sphere, a layer of the liquid should get intact, and this should not fall. Means should not slip. You know about slipping in rotational motions and all, right? So there should not be any slipping between the fluid and the sphere. So this is the environment we need. Here we are talking about a solid thing falling through a liquid, but we can also apply this to a liquid falling through a gas, right? So here actually the thing will be something like, we can calculate velocity, we can calculate, we have these constants, we have these densities, and now from this we can calculate radius of the liquid. Means suppose we are dropping a liquid drop, we can calculate what will be the radius of the drop falling through a particular gaseous medium. Or from this we can also calculate, suppose we are dropping a water drop in air, we can calculate the radius of the water drop. And this method was also used in Millikan's all drop experiment, from which the charge on electron was calculated. You can study about it more and comment it below. So this is for today. We will talk about more experiments and more about labs in our upcoming lectures. Thanks for watching.